in terms of what is it that we are trying to recover. As I said before we dispersed for lunch, we talked of energy recovery, we have talked of nutrient recovery, and now we will deal with another class of contaminants. Contaminants in the sense that they are present in a matrix, they are undesirable, but as you heard on the very first inaugural session from Dr. Kumar, that nothing is really waste. In our case, these heavy metals become a resource. But before I do that, um, do you have any questions based on what we have covered until now? Yes.
This top low light.
Yes.
I would like to know in case of this no mix toilet and in case of septic toilet, what was the performance of this neopto light in recovering how much, basically how much ammonia could it recover, and what was the efficiency of this or geolite?
Its capacity, the data that I presented was about 5 milligrams of ammonium nitrogen per gram. But since this PowerPoint, we have worked a little more. We have done a few different kinds of preliminary treatment. Now, I think the latest data that my student sent me over email is about 10 milligrams of ammonium nitrogen per gram. That is the capacity. And the regeneration, I think we are about 88 to 90%. But as I said, there is this tail which is kind of a, what to say, bit of a challenge.
I guess there will be some significant difference between the performance in case of septic tank and in case of no mix toilet.
Well, in case of septic, no mixed toilet, of course, we have not done anything. It was just an idea that I did. Septic tank, what happens in septic tank is, as you can imagine, the degree of suspended solids is so high that even if we say there are these three zones, there is the solid and there is the liquid and there is the scum, the liquid is still full of suspended solids. So, what we found is in the septic tank, it was nowhere close to the capacity that you get in the lab.
Something actually, what was coming into my mind because I work on septic tanks. So there is a lot of solid in suspended solid in septic tank water. So I think the geolite will get exhausted very soon because like suspended solids will get accumulated along with the geolite in the, and that may probably affect its efficiency to a great extent.
Yeah, possible. I mean, we have done only, as I said, one run in a septic tank. But more than suspended solids, what we found is there are some other contaminants in the water. We don't really have a full idea of their composition, which I think these are organics. These are fouling the zeolite. So the zeolite turns a very blackish, brownish color, and no matter how many times you regenerate, that color doesn't go away. So the zeolite, it seems as if it is permanently coated with some organic. Now, as I said, we have not really done repeated tests in the septic tank. That means we put in the septic tank, we take it out, regenerate again, put it back, then see second time what is its performance. We haven't done that. But this is more of what is called as proof of concept. But yeah, you were asking something before I interrupted.
Since we are treating human disease, so if we can treat parallelly the liquid part also with this electrolyte, our system, that will be actually great. That's why I wanted to know that what is the efficiency of this light and how much it can really work upon.
Yeah.
So if we do it on a field ground basis, then if like we have some discharge limits and those things. So how much does it recover? Whether it will have some value or not? That is very especially important in case of India, because whenever government will be asking for like we ask for some funds or anything, they will ask first what is the value you will get out of this resource. So that is essentially important for me to know if I install the system whether I will get some money out of it or not, which will at least contribute to the operational cost. If I cannot sell, that is not an issue, but at least the operational cost.
I perfectly understand, and it's not very different where I am either. The point that we try to make to these bureaucrats, and we have bureaucrats in the United States as well, don't think that we don't have to face them. The point that we try to make to them is, see, you have to treat the water nevertheless. No matter what you do, you cannot discharge this water. So if the treatment cost is X dollars per unit volume of water, now only thing one has to look into is by doing this, you are spending more than X. Can you recover this delta? That's the thing. I mean, as you said, and this is universal. There is not a way in which you can kind of generate a product that will not only cover all the costs but will now have an economic benefit. It doesn't really happen like that. In the case of phosphorus, for example, constantly we are told that phosphorus fertilizers are so cheap. Why should we go into all this complicated technology to generate few kilograms? And the answer to that is, right now it is at a scale where we are talking only of a few kilograms. But if the stars align and if, let's say, a big treatment plant tries this out, then it can be scaled up very fast. So cost is always a very tricky question. What happens if you look at any technologies, initially when the technology is introduced, the cost is kind of prohibitive. But as it becomes more and more acceptable, as it gets into the market, as its prevalence increases, the cost drastically reduces. So we are right now at the very, very preliminary stage. So right now it's kind of difficult to talk about cost. But of course, we always try to tell these bureaucrats that that's not the way to look at it. Of course, they have their own compulsions. They say, well, this will go to the ministry, this will go there, and I have to convince my bosses. And all that is true. I'm not at all doubting that. But if they buy this idea that they should not be looking purely at the cost, they have to look at whether present technologies are able to meet these objectives, which they are not. So something has to be done, something has to be tried out. And if they are unwilling to give few dollars to try it out, then they can forget about all these grand promises that they made. So it's a convincing. I mean, one has to try to convince as best as possible.
After that, the septic tank, like this is being installed like for every house. So if we can really generate some significant amount of ammonia, so this will be like in metric tons, a million tons, because every day if 135 electricity also is considering, at least 70 to 80 is in flushing and those two. So a significant water will come out, and if you can recover some kind of ammonia, if it can contribute to the whole process, this will also convince the people to a great extent.
Absolutely, but as we have seen with other similar cases, when we talk of individual residence level, one has to put this in a package such that the owner is not at all involved in any of it. And we have seen that, I mean, we will talk about silver on Friday, I believe. Yes, Friday. So with silver, we have seen that if you put it in an individual house, after the laundry machine, after the washer. Um, Again, it's a cartridge kind of an approach. It has to be such that there has to be a sensor which will tell that yes, this cartridge is now being exhausted. So for ammonium and phosphorus, it's very easy to build. Ammonium sensors are presently available in the market as such. So that's not a big thing. Phosphorus we can tweak a little bit. So the thing is, for a house owner or for even multiple house complexes, it has to be a technology which basically you have, let's say, two cartridges. Flow is going through one. The moment the sensor says an alarm or that it is reaching its capacity, the flow automatically has to be diverted to the second one. And this one, you just take out the cartridge and you bring it to a facility which collects it, and then that is sent to a central regeneration facility. So one has to think of all these things before it's ready to be implemented in the market. But you are very correct. I mean, these are tiny, tiny numbers, but when you multiply by huge number of units, the final product is not insignificant.
These are the things we have been facing from a lot of them. Get funds to convince them.
Exactly, and that is universal. That challenge is universal. Any other question? Okay, so we will look at now heavy metals, and I will base today's discussion on a chapter that we wrote, I think, many years ago. Um, and Today we will talk mainly about the chemistry in terms of, well, how do heavy metals interact with an ion exchanger? What kinds of stability constants are we looking at? How do we decide what would be the best oscillating exchanger for a particular heavy metal, so forth and so on? Tomorrow, I will try to give you some idea of the morphology. So, until now, whatever we have talked about in terms of ion exchanger, it has always been a bead, a spherical bead. But it doesn't necessarily have to be so. We now have technologies, very mature technologies, which can generate fibers. For example, submicron fibers. We'll talk about that tomorrow. We can put very tiny beads in a Teflon matrix and generate a sheet. And of course, in ion exchange, there are these membranes. Ion exchange membranes are very mature technology. So we can look at some of these morphologies. So the first thing that we need to keep in mind is when we are looking at heavy metal separation or removal or recovery, almost all the time we have a situation where the heavy metal, that is the contaminant that needs to be removed, is at a much, much lower concentration than some of the competing metals. Okay, so if I have industrial wastewater, let's say, it's very common that I am trying to remove, let's say, copper from it. But that copper typically would have to be removed against a background of much higher concentrations of sodium, magnesium, calcium, etc., etc. So again, the idea is that selectivity becomes very important. Okay, so we have to make selective process. That's the first thing. And the second thing is, when we go to the polymer, the exchanger, then we have to look at some of these variables. Okay, so what is the polymer, or what is the starting polymer? And we typically have either polystyrene or polyacrylate. And then the question is, these polymers, of course, how do you make a polymer? You start with a monomer, you initiate a reaction, and it starts to polymerize. And then when you get to what you want, you then have to terminate. So there are these three steps in any polymerization process. So the initiation, of course, you have to bring in an initiation agent, and then what happens is you have to cross-link, because the polymer, if you have just a linear chain, it will not have any strength. So what you have to do, you have to make it three-dimensionally robust. How do you do that? You do it through cross-linking. So that cross-linking, what is the cross-linking agent? So for example, if you start with the polystyrene, the most common cross-linker is a divinyl benzene, but doesn't necessarily have to be that all the time. Now the question is, what is the percentage? Because what happens is that if you, let's say, put in too much of a cross-linker, the 3D structure that you get will be very robust, but you will lose its equilibrium capacity, because now so much of these sites are now difficult to reach because you have such a dense kind of electrolyte solution. On the other hand, if you have too little of a cross-linker, then your sites are available, but the polymer will not be able to resist, let's say, any shock changes or things like that. So what happens in a polymer is, let's take the case of a bead. A bead is a sphere, okay? So just imagine it's a ball, but inside the ball there is a very, very strong electrolyte solution. Okay? Now, when you put this polymer in a column, for example, or when you now start passing a solution, these polymers, they swell and they shrink because of this osmotic pressure difference, as you know. I mean, inside the polymer, there is a very strong electrolyte solution, so it has a very high osmotic pressure, and outside it is much less. So water will try to get in to even out this concentration gradient. That's what osmosis is all about, and so the polymer will swell. Now, if you have packed the polymer in a column when it was, let's say, this size, and now you pass the water and the polymer starts to swell, you can imagine it will create all these stresses on the column. So that's a problem. And then when you have a swollen polymer, and now if you pass an acid, again, because of some very basic chemistry, it will now shrink. And so a polymer swelling, shrinking, you need to have the elasticity for it to be to absorb all that. Otherwise, if you don't build it right, one cycle of swelling and shrinking, the polymer will kind of become useless. So we need to keep all these things in mind. And then perhaps the most important would be, what functional group do you put on this polymer? What is the interaction of this functional group with the heavy metal? And of course, porosity and concentration also play a role. So we will look into these things as we progress, as our discussion progresses. So Arpan will send you this file after today's class, and you can, I mean, it's a pretty thick chapter. So it starts on page 45 and ends on 92. So 92 minus 45 is how much? 47, 48 pages. So I'm not expecting you to read all the 48 pages before tomorrow, but if you read the first 10, 15 pages, let's say for today, you'll have a pretty good idea of what we are trying to achieve in terms of finding the right volume. Okay. So we talked about swelling, shrinking. Now, with heavy metals, the main thing is to keep in mind is that the heavy metal is a Lewis acid, right? And so your chelating agent, which is inside the ion exchanger, that is a Lewis base. And so this Lewis acid, Lewis base interaction is the governing interaction that gives this selectivity. So we need to keep that in mind all the time. So, for example, you see here a styrene, chain, polystyrene chain, and we now have put in a benzene into one of these, and now we have put in this functional group. This functional group is called immunodiacetate. So why is this functional group very popular? Well, as you can see, it has a nitrogen which can donate a lone pair of electrons, and it has these two oxygens which also have a lone pair of electrons. And so now, if I let me draw it out for you that way, I think. And I'm not writing the top thing, I'm just writing it purely in terms of this functional group that you see. Now, let's say you get this polymer, it is very widely available, it is heavily used in the industry. So, you buy this immunodiacetate polymer, it comes typically where, I mean, it cannot stay like this, right? I mean, here you have this negative charge. So this negative charge has to be balanced by something. So let us suppose for our discussion that it is balanced by Na plus. Okay. Now imagine that you now bring this polymer in contact with a solution which has, let's say, lead. You want to remove lead. So what will happen is that if lead ion is passing through this column, lead, as you know, it's a very strong Lewis acid. So what happens is that what you will get here is that the lead will come in, the sodium will come out. That's right. But let's look at the stereochemistry and the coordination chemistry, which are much more important. So I'm just so you see that the case of lead is much more preferable. Why? Because number one, lead is divalent. So lead now has to bond with these two acetate groups, and that is how the charge neutrality is satisfied. And as you can see, lead 2 plus has much more charge density than Na plus. And not only that, this lead can accept a lone pair of electrons from the nitrogen. And that is what gives this chelating exchanger the selectivity that is needed. So in your water, you have lead, you have calcium, you have sodium, you have magnesium, you have all these others. Now, these are what we call benign ions. In the case of heavy metal decontamination, we are not interested in removing calcium or magnesium or sodium. They can stay in the water or in the wastewater or whatever. Keep in mind, this is very different from our discussion yesterday when we were looking at softening water. If you have hard water, then you are removing calcium, magnesium. We are not talking of that right now. We are trying to remove lead. And what is very probable and possible is that lead concentration, let's say 5 milligrams per liter, calcium 100 milligrams per liter, sodium is 250 milligrams per liter. Okay, so it's not only a challenge to remove lead, but it is a bigger challenge to remove lead which has a much lower concentration than its competitors. So because of this, we need the functional groups to be such that they provide the additional advantage from the coordination bond besides just the Coulombic interaction. So this is just Coulombic. This 2 plus is just Coulombic with this oxygen providing a lone pair of electrons, this oxygen providing a lone pair of electrons, this nitrogen providing a lone pair of electrons. These three together make this the ideal chelating exchanger. Okay, so
So in
yes.
this case, then if we calculate the energies, so total energy will be Coulombic interaction plus this
Acid test, yes, yes,
chelating.
yes.
So if we want to find the K equilibrium, then K will be equal to K electrostatic plus
K will be
the equilibrium constant. K will be K equal to K electrostatic plus K ligand.
no, not K. The delta G will be equal to delta G plus this. K will be the product of these two, right?
Then product equal to product of this.
Exactly. Okay, so as I was saying, the cross-linking plays an important role because cross-linking is the one that provides this 3D rigidity. So you have this linear chain. Now, to bind these linear chains, you need this cross-linker. Okay? So you have this linear chain, you have this linear chain, and you have this cross-linker, divinyl benzene, for example. So, in a typical ion exchange reaction, cationic or anionic, the type of interaction between the functional groups on the polymer and the exchangeable liquid phase ions is primarily electrostatic or Coulombic, and the selectivity of the ion exchanger for a target ion is governed by the hydrated ionic radii, the charge compared to the competing ions, hydrophobic or hydrophilic nature of the polymer matrix. So it so happens that, as we said, the two most common backbones, polymeric backbones, are polystyrene and polyacrylate or polymethacrylate. So polystyrene is much more hydrophobic. And polyacrylate is much more hydrophilic. Now, of course, everything is in relative terms. So the hydrophobicity or the hydrophilicity, they play also a very important role in terms of, because as you can see, if the, okay, I'll come to that in a little later, I think, maybe jumping ahead. And so the hydrophobic or the hydrophilic nature of the polymer, charge density and steric property. So the steric property is what makes this a very manipulable system. In other words, if you can, it's a big if, I admit, it's a big if, but if you can create the right steric hindrances for competing ions, then you can achieve very high selectivity. How do you do that? I won't be able to get to that discussion the time that we have, but I can only say that for a long time, at least for 30 years, let's say, until about 20 years ago, for a long time, we were trying to develop an ion exchanger which was nitrate selective. Okay, so nitrate is a problem in many groundwaters. So you have a private well in your backyard. You want to pump that water from that well for your house, and suddenly meaning everything was running fine, but now you start seeing nitrate in your groundwater. And the reasons are fertilizer runoff, etc., etc. So what do? You can't abandon the well. And removing nitrate is not very easy. So if you have a water which has iron, let's say, which is very common, and iron, as you know, iron and manganese, they go together. If you have a water which has iron and manganese, removing iron and manganese is very easy. There are so many technologies. Um, if you have hard water, removing hardness very easy. But if you have, let's say, 10 milligrams per liter of nitrate nitrogen, and you want to remove just that nitrate, the rest of the water is fine. Very difficult. There is no technology which can selectively do that. And what people do is they just put an RO. And RO is kind of a kill-all technology. RO is not selective, as you know. All RO does is that it just stops all these ions from going through. Now, you just want to remove the nitrate, but now you are blocking everything. And so it's very laughable, but very true that I know of cases where they had this problem of nitrate in the groundwater. They put in an RO, and the RO, as I said, it stopped almost all the ions from passing through. So the permeate from the RO was, let's say, very good quality water. But because it tasted so bland that they then had to put in some minerals into it. Because if you drink this water, if this is perfectly pure distilled water, you wouldn't want to drink it. It will be tasteless. So you do want some minerals in the water. So I think they made the problem much worse than original. The problem was to remove 10 milligrams per liter of nitrate. They removed 10 milligrams per liter of nitrate plus everything else, sodium, calcium, everything else. Not only that, RO, as you know, you can only get a yield of, let's say, 50%, 65%, 70%. So 30% of the water is now much, much more concentrated. What do you do with that? You just push it into the sewer system. Sewer systems are not put in to handle these high concentrations of these ions. Sewers and wastewater treatment plants were put in to deal with organics and things like that. So you put 30% of this water into the sewer system, or it has to be disposed of. And for the remaining 70%, you now have to add minerals from outside. So it's a very stupid kind of an idea. But what I'm trying to say is that because there is no accepted mature technology that removes just the nitrate, people started looking into ion exchanger. And ion exchanger, as you can imagine, you can't really have a chelating exchanger, because chelating exchangers, they only work if your Lewis base is a very strong, if the ligand is strong. Nitrate is perhaps the weakest ligand, right? So how do you remove nitrate? How do you make a selective resin selective nitrate? So what people started to do was they couldn't do much in terms of the hydrated ionic radii. Nitrate is just, you cannot do anything to that. This thing, yes, you can play around with the nitrate, as you know, is extremely hydrophilic. So if you come up with a polymeric matrix which is very hydrophilic, you get some benefits. But those benefits can't really stand the competition from chloride and sulfate and all that. So what you can do is you can create a steric property such that only nitrate will go. And that's exactly what they did. They made this polymer so dense that only nitrate could enter, its competitors could not. And they were able to, this nitrate selective resin, Cybron, it's the trade name SYBRO, and Cybron resins, they were the workhorse for many years, definitely for 10, 15 years. But there are these problems. The resin, first of all, is not very well regenerable. Its capacity for nitrate removal is not very high. But this is one case where you have to come up with the resin only which would do the selective, which would have the selectivity property based on the steric property. Okay. Anyway, we are talking of heavy metals now, so let's move along. So as I said, we are looking at competition. So the concentration of the background non-toxic ions is much higher than the target heavy metal ions. So if you do a typical equilibrium constant, so you have a resin which is in calcium form and you're trying to remove nickel. So the resin binds to the nickel, calcium comes out. And the equilibrium reaction, or the equilibrium equation would be this, right? And this is, both are divalent. So if this is a normal exchanger, then there will be no real preference of that resin for nickel over calcium. Okay? So that's exactly what we see. If you take what we call a strong acid cation exchanger. Strong acid cation exchanger means that you take this polymer, polystyrene, and then you put in a sulfonic acid functional group. So this is this famous resin which has been used for demineralization for more than 50 years, I would guess. And it sells in tons because many industries need the kind of demineralized water or ultra pure water. So it's a very popular resin. That's all I'm trying to say for cation removal. But if you are looking at its selectivity, let's see. So these selectivities are always based in terms of hydrogen. So this is all relative, as you can see. So hydrogen is always 1. Okay, as compared to hydrogen, sodium is 1.5. Well, you can see, I mean, 1.5 is not very different from 1. But let's go to divalent species, okay? So iron, ferrous, that is, Fe2 plus, 2.55. Zinc, 0.7. So this resin would not be suitable one for heavy metal removal, right? Because it has no real selectivity. Copper, 2.9. Lead is little different. This could be, you can say that this is fine for lead, but not really, because when we try to remove lead, we see that we need selectivities, not 7.5, but maybe 75, 10 times more selectivity. Only then does it really become economically feasible. Okay, so the point that I'm trying to make is that this resin, strong acid cation exchanger with sulfonic acid functional group, will not be suitable to remove zinc or cadmium or copper or cobalt or nickel, because it doesn't have the selectivity. Why doesn't it have the selectivity? Well, the sulfonic acid functional group, it has no ligand actually. The only way in which the interaction occurs is Coulomb way. There is no scope for any Lewis acid-base interaction here. So if there is no scope, how can it be selective? That's the idea that I'm trying to convey. Okay. Then the next problem is the capacity. Okay, so we typically, the commercial ion exchangers that you get in the market, typically all of them come with this range of capacity. Let's say 2-3 equivalents per liter. So 1 liter, we are looking at a volume. 1 liter of the resin can have, let's say, 2, 3, 4 equivalents. Okay. And so when this capacity is exhausted, you need to regenerate. And first of all, with this kind of capacity, you have to regenerate very often, frequent regeneration. And the second thing is, if you look at this resin, sulfonic acid functional group, how would you regenerate it? Well, you will say, okay, this is strong acid cation exchanger. If at all, I'm using it to remove nickel, let's say, I will put the resin in sodium form, very good. I will bring this solution which has nickel, and it is twice as, and nickel is 3, sodium is 1.5. So let's say you are able to do nickel removal, partial nickel removal. When this bed is exhausted, how would you regenerate this resin? What would be your ideal regenerant? NaCl, okay? Because it's a strong acid. Now, when you put in NaCl, you will see that in order for you to reverse the selectivity, you have to put in a very high concentration of NaCl. Okay? And there are these problems of a very high NaCl concentration. First of all, the osmotic pressure difference, as I talked about. And then when you are able to strip out the nickel, this nickel is now against a background of very, very high sodium chloride. So then there are these problems as well. So what I'm trying to say is this is not a right resin. So that's when in the 1960s, you can say, people started looking at chelating exchangers that are metal selective. And when we say metal selective, heavy metal selective, we are looking at primarily at these 6. And you can add mercury to it, but in general, these are the ones that you've encountered most often. Copper, mercury is already there. Copper, mercury, lead, nickel, cadmium, zinc, and I missed from here cobalt, and what else did we miss? Strontium is not very wrong. Anyway, so let's just concentrate on this. And within this, mercury, if you have to remove mercury, it's a little different than removing copper or lead or nickel or cadmium or zinc. Let's just say for the time being that our heavy metals that we want to remove are copper, lead, nickel, cadmium, or zinc. Let's not put in mercury right now because mercury is a little different. Of course, it's a heavy metal, no question about it. And then there are some which exist as anions. So we will not talk of these. We will talk only of heavy metals which in free form are all existing as anions. So as I said, we start looking at chelating exchangers, and the most common chelating exchanger for heavy metals is this one, iminodiacetate. Why? Because as I just explained. Okay? Now, how do you synthesize an iminodiacetate resin? Well, it's a little involved, so I will not get into synthesis chemistry. We just don't have the time. But the point being that we have to think of all these things when we decide on a certain resin. First of all, how do we make it? Now you can say, well, I can buy it, and yes, it's available, but we still do need to think about the impact in terms of how hazardous wastes are generated when you make this kind of a resin, and you make a more sustainable process, etc., etc. So, let's look at figure 3.4. So, use the right. So, what is this figure? This figure says what is the experimentally determined heavy metal calcium separation factor for a picolylamine functional group or a thiol functional group or iminodiacetate. So these three, you can say, are the most common chelating exchanger. And of course, just the regular acetate, the acetate group. So Immunodiacetate we just talked about. Why is it selective? Then thiol, as you know, is sulfur based. Sulfur also has this capability of being able to donate lone pair of electrons. And so with sulfur, what happens is that it is very good for mercury removal. So if you have a situation where you have to remove mercury, and we deal with mercury removal mainly in dental offices. If you're looking at industrial wastewater, of course, if the industry uses mercury for some reason, jewelry, for example, very common. Uh, the work that we did, we were looking at dentist offices. In the dentist office, when you do these fillings, when you have a cavity in your tooth, then you fill it up, and one of the things that they put into this filling is mercury. So there is some mercury generated, and we were trying to remove it. So when you have mercury, if you have to remove mercury, then perhaps your best choice by far is the thiol functional. Whereas if you want to remove copper or lead or zinc, you have many more choices. And so you see, for example, let's see, copper, calcium for GD73. You see, the pH plays a very important role. Why so? Well, you can guess, because when we're looking at the thiol functional group, the SOH will, when will it become SOH and when will it be SO minus? So those kinds of things, they become very critical, right? So I'd like to spend more time on this. So when we talk of heavy metal removal, chelating exchangers, these are typically our choices. I mean, people make new resins all the time, and you can make some resin for some very specific purpose. But in general, if you're looking at commercially available resins, these are the functional groups that we use most of the time. So this one is the carboxylate, the simplest one. All it has is a carboxylic acid group, CO minus, and so it has one oxygen, which has this pair of electrons that it can donate, and this one oxygen atom. And of course, the matrix can be polymethacrylate, it can be polystyrene as well. Mostly it is polymethacrylate, okay? So you can see that if I want to remove a heavy metal, then this oxygen will provide the Lewis acid. Okay. Then we talked about immunodiacetate. So here it is not only this oxygen, but this oxygen and this nitrogen. Now, keep in mind that the higher the number of sites where it can bind with, the more selective the resin will be. That is correct. But we also have to think of the reverse. When you bind the heavy metal to the functional group, after that you have to get it out as well, regenerate it as well. So there is always a trade-off. Sometimes what we do is we make resins which are only for the exhaustion cycle. We don't regenerate them. The most common one would be the resins that are typically used to remove perchlorate. Perchlorate, as you know, we get perchlorate wastes, especially from explosives. So if you have, let's say, as we do, 4th of July, we have a lot of fireworks. So these fireworks, they use this perchlorate as a propellant. Okay? So you have all this firework, but then the soil, I mean, all these fireworks, they are not from some place. They give all these flares and all this beauty, and then they land. And typically, the soil that they land in then becomes infected, contaminated with perchlorate. So we may have to go and remove. So when we have to remove perchlorate, perchlorate is a very difficult ion to remove, and so none of these would work. What people then decided is to make a resin, and I'll not go into the synthesis because we just don't have the time. But the point being that we made a resin such that it will be extremely, extremely selective for perchlorate, but it will never be regenerated because we are dealing with so small mass of perchlorate that we have to remove. That and perchlorate is such a dangerous contaminant in terms of health effects if you drink perchlorate in contaminated water, because we have to remove that. The necessity of removing is so high that we don't really regenerate the resin. These are called once-through resins. Once through. Once through means, as the name suggests, once through. So let's say you do a column mode. So you pack this resin in a column, you pass your perchlorate contaminated water. When this resin is exhausted, you just kind of, the disposal, that's a whole different scenario. But yeah.
Sir, if we regenerate it by swaying the pH, suppose sir, if we use the carboxylate group, COO, so it is a big acid.
Yes.
So it will be working environment with higher pH.
Yes.
During regeneration, if we lower the pH, then obviously it will.
Yes, that's exactly what we do. Yes.
So is this so for heavy metal also we can do it?
Yes, yes. We do this all the time for heavy metal. I was talking of a very, very specific situation where we make a resin which is not regenerated. And with perchlorate, that's the ClO4 minus. But I'm not talking of heavy metal. Sometimes we have to make resins which we are not interested in regenerating. But still the need is so dire that remove the contaminant, even a once-through resin is fine.
Another question is that, sir, during synthesis of resin,
yes,
our main focus is only the functional group first.
Functional group, how do you place the functional group on the backbone and whether these functional groups are reachable or not. Yeah.
And sir, we select the functional group that affinity of this functional group towards the heavy metals. It means we select in this way. Suppose I have to remove lead. Suppose I assume that this functional group is more selective for lead. If we insert this functional group in matrix, then it's become selective for this lead.
Yes.
We just means initially we architect this model, then we synthesize it.
Yes, absolutely. Absolutely.
So sir, if I want to synthesize the resin, I have to first think about the functional group. Then we have to use some. I think we have to use some material and means salt or acid to extract this functional group or insert the functional in the matrix. In this way, sir, company synthesis, or is there any other way?
No, you are very correct. But there is also an art. It's not just all science. So these companies, these resin manufacturers, the Dow Chemicals, the Roman Haas's, what they have done is through years and years of experience, they have been able to perfect. Because if you try to make a resin today, even if you are the best chemist in the world, chances are you will fail many times before you come up with the final. Because these companies that make these commercial resins, they have gone through so many trials that now These resins, I would not want to make them in my lab. Why should I? Because they are available so easily. But as you said, if I have a very unique situation where none of these would work, then I have to, if I have to make one, then yes. So, perchlorate is one, nitrate selective resin is one. These were specific situations which warranted the synthesis of a new resin. But if I have heavy metal, then what we typically do is we look at our matrix. Now, I talked of nickel, I talked of lead, but with hazardous waste situations where you have a site which is now contaminated with heavy metals, then it's not just one heavy metal that comes. We get 4, 5, 6 heavy metals at different concentrations. So then we have to decide how to choose, and maybe not choose just one, but more than one, so that we know what to remove. In other words, let's say I have a site where they would pour battery waste. So in the past, lead acid batteries were the only industrial scale batteries. So lead acid battery, as you know, when the battery is exhausted, people would just dump. And there were companies which would try to extract the lead, but they would dump more than how much they would extract. And so we have what are known as battery acid sites, many in the United States, where acres and acres of land, not just the land, the groundwater, the Vados zone, all of that is now contaminated with these. So in such situations, what do you do? One very common way is we excavate the soil. We then put the soil in an acid solution. All these heavy metals come out of the soil. We then take the clean soil, put it back in, and now we have a solution where, let's say, we have 5 heavy metals in an acid solution. Now, it so happens that many a time and these 5 heavy metals are not in comparable concentrations. Their concentrations may vary. So then you have to decide what is your most important heavy metal that you're trying to remove. And can you live with, let's say, few milligrams per liter of heavy metal Y still in the solution? So such cases, then you have to go look at the binding constants and then decide which one should I choose to remove which particular heavy metal. That's one part. The second part is even more challenging and intellectually more stimulating. That is, you have 5 heavy metals in your acid solution. You have to remove all 5. Very good. So you put this in an chelating exchanger column. You pass it through. All those heavy metals are removed. Very good. Now you regenerate the resin. Regenerate the resin. The 5 heavy metals come out in a much stronger solution. How do you recover individual heavy metals from these 5? Very challenging.
If I use the column in series.
But in series, what would it be different?
Sir,
You have all the 5 in your solution. Putting in series, how would it help?
initially I put for lead removal. Suppose for specific selectively for lead, I use this functional group to make fast result. Then whatever the effluent comes.
No, but even if you have a resin that is more selective for lead, it doesn't mean it is zero selective for copper, cadmium, nickel, and all that. So that resin will also, it will have more of lead, but all the other 4 as well. We'll talk about it tomorrow. So I want to.
So done practically like 1 acre of land and you want to take out the whole soil and do digestion and take out the individual. Do you think be a very hectic task to do.
It is, but what can you do? We have all these what are known as superfund sites, which are so heavily contaminated that the federal government has to come in because it has become unsafe. Now, keep in mind, the practice may have happened 50 years ago when there were no regulations. People didn't know the, the harmful effects of what they were doing. And that site, it was owned by Company X. Company X went out of business, sold the land to Company Y. Company Y went out of the business. Now there's a school. This is exactly what happened uh, in a town very close to Niagara, the Niagara Falls. Uh, exactly. So, if you have a situation where your site is contaminated and it is a very bad contamination scenario, you have no option.
So, in that case, the whole soil will be excavated, like for 3-4 meters.
Well, we don't, I shouldn't say the whole soil, it's what we are calling hotspots. So, if you look at the contamination is typically not uniform. You have these zones which are extremely contaminated. So, those are the ones that you attack first.
1.3
Pardon me?
1.3 method.
Yes.
And other processes are also there.
So, this is soil. So, you have to pump and treat, you have to then pump a solution which will then extract these heavy metals and then bring it out and treat. So the thing is, there are basically two ways of dealing with this. One is ex situ, that means you bring the soil into a reactor, extract, and you put the clean soil back, and the other one is in situ. And there are some in situ methods. We will not get the time to look. But I will try to give you a little bit of a flavor tomorrow as to what kind of morphologies are more suited for in situ. I mean, you can't do in situ with the column, right? With the resin spherical bead. So you need a little different morphology. Questions? Any other questions?
So, if these columns are used in situ, what will be like where they will be placed?
How can you place this column in situ?
You are saying that you also can use columns.
No, I didn't say use the column. Use the material. Use the same concept, but the contact has to be done differently. Yeah.
In that case, some solution will be passed and then it will be collected.
We will talk about it tomorrow. So just give us 12 hours or whatever hours, and your question will be answered. Okay, so so we talked of this is the most basic one. Most basic one means this is the one which has only one oxygen, which is the electron donor atom. Then we can have aminophosphate, as you can see, nitrogen, phosphorus, oxygen. Then we can have, this is the Day-3, and remember I was talking about the other day when we were talking about phosphorus. This is the starting resin that we use, into which we then put in iron oxyhydroxide or zirconium oxide or whatnot. And we can have, this is known as Day-2N, this is pyridine based, or we can have thiol, which is what we typically do for mercury and sulfur. If you have, silver. If you have to remove mercury and or silver, your first choice would be a thiol. Now, please don't think that these are all that there are. There are many more, but we have come up with this list because you can say more than 90% of the cases, these are the ones that we use.
Sir, for hardness removal.
Hardness removal, okay.
Sir, we can use carboxylic group as well as sulfonic group, functional group. So, which one will be better, sir?
Well, for hardness removal, most of the time we use a strong acid functional group because the typical concentration of calcium and magnesium in the water is such that uh, that it kind of helps us in the exhaustion process. And even though we have to put in kind of a high sodium chloride regenerant, it's the amount is not a huge amount. So of course, disposal one needs to think about. But if you have, let's say, seawater kind of total dissolved solids into which there is elevated concentration of calcium and magnesium, it's not a big problem. But what you can also do and what people have done is you can also use a weak acid resin, and in that case there are certain advantages in the sense that regeneration is so much better because you just have to reduce the pH, and if you bring the resin back in H plus form, but then you have to do another cycle where you have to go back in and replace the hydrogen with sodium. So it's a two-step regeneration process, whereas a strong acid is just a one-step. Okay, so yes.
Capacity of weak acid or base is higher compared to
Is what?
Capacity of weak acid or weak base exchanger has high capacity compared to strong or strong base or
Strong acid cation exchanger has more capacity than weak acid
weak acid.
in general, unless you go and okay. So if you look at a strong acid resin, then strong acid resin doesn't really care about the pH. So when you titrate, then you get this very classic. Whereas in the weak acid, as you know, because it has this affinity for hydrogen, the pH plays an important role. So that's why when we deal with a strong acid resin, we have no problem with any, I mean, it will work in any pH. But if you want to use a weak acid, let's say for hardness removal, as we just heard, then you have to be very careful. What is the pH that you are using in the exhaustion cycle? And now you may have to manipulate the pH because if your, let's say, alkalinity is very high, then you may have to do certain manipulation. But with strong acid, there is no problem as such. And so you know that this is this famous equation that the pKa is nothing but the pH minus the log of the aqueous phase anion concentration and plus log of the total concentration of dissociated anion. So this is, again, this comes straight from aqueous chemistry. When we titrate, especially in this case of titration of solid phase with an acid or a base. So we can use this formula to get a sense of our pKa. Because keep in mind, pKa of a resin with carboxylate functional group will not be the same as pKa of acetic acid. It will be close, but it will not be the same. Okay? So we need to go use this formula. And we have to find that through titration typically. So all right. So this figure basically tells you what kind of binding you get. Let's look at the caption. Nature of metal ion binding, cation exchange, followed by chelation. So you have to satisfy the charge, of course, charge neutrality, I mean. But then, because of the chelation, you get the selectivity as we just discussed. So keep in mind that the metal ion is surrounded by the coordination. I mean, that depends on the coordination number. It's surrounded by water molecules. So you have to expend some amount of energy in displacing these water molecules so that you can then bind with the Lewis acid. So Lewis base, sorry. So in the case of aminophosphonate, one oxygen, two oxygen, one nitrogen. In the case of aminodiacetate, one oxygen, two oxygen, and nitrogen. But you see that these two, this nitrogen and this nitrogen, even though it's a nitrogen, in terms of steric hindrance, you can see that this will be more difficult to form this bond than this bond, right? Because there's all this, so the steric space this will be much restricted. So all I'm trying to say is that there's a lot of factors that go into. And if you look at just the regular carboxylate, which is by far the most common, then it's very, very straightforward. You have this oxygen, you have this oxygen, and minus, satisfied by this plus. Okay. And so we have discussed this before, but not a bad idea to repeat that. The selectivity comes from the fact that it is a combination of Coulombic and coordination. And the delta G would be the delta G of the Coulombic plus the delta G of the coordinate. And so the K would be the product of it. Now, when we look at carboxylate functional group, then we see, now what we typically do is that we look at what is the order. That means between the heavy metals, which ones are more selective. So based on these references, we can say that for carboxylate or even for aminodiacetate for that matter, this is typically the hierarchy. That the lead is always much more selective. Lead is more selective than copper, which in turn cadmium, zinc, nickel. Why? It's a very easy answer. If you just look at the electron orbital, you will see the vacant D subshell. Okay. So I'll just skip that. And so the other thing is, how do I get the separation factor values, and how can I have some estimate of the separation factor values? And the best way to look at it is, well, I can find the binding constants in the liquid phase. This is available through that very famous series of critical stability constants by Martel and Smith, the 4-volume. It's a treasure trove, basically. It lists all the aqueous phase stability constants that you can come across. Okay. So, aqueous phase is no problem. What you can do, and what this graph tries to tell you, is that there is a very straight, very linear relationship between metal separation factor for carboxylate resin and the acetate metal stability constant. Okay, so you see, it's very good fit. So in other words, you can be assured, all this is trying to say is that you can be assured that the copper will bind much more than zinc. All I'm trying to say. So we are getting close to 4 o'clock. I will just go over a few quick things and then we will be done for the day. Um, okay, so as I was mentioning, cross-linking is very important because it provides the three-dimensional rigidity, but cross-linking comes at a price. And as you can see, what it does is that it drastically reduces the diffusion coefficient. Why? Because now it becomes so much more difficult for these ions to go through. They face so much steric hindrance. So this classic Boyd was perhaps the uh, the most well-known physical chemist ever. Okay? And in the 1950s and 60s, the pioneering work that he did, even today we practically just use the same references, okay? So he showed how when I increase the cross-linking, I pay this price with diffusion coefficient, correct? And how do we get these diffusion coefficient values? It's very classic partial differential equation, which I'm sure you have uh, seen and done. This is the same model which we use for adsorption as well, interparticle diffusion. And there is this very famous book, Mathematics of Diffusion by Grant, and it has all the analytical solutions. So I will not get into the details. You can get these diffusive. Keep in mind, this is not diffusion in the aqueous phase. This is diffusion in the exchanger phase. So it's very different. But to these experiments, you can get them very easily. There is another model which we have to use many a time, and that is based on the self-diffusion coefficient of a counter ion. This is an equation that use. This is based on much more recent work, Yoshida and Kataoka, and there is a little difference in the assumption. This is assumption of parallel diffusion of counter ions. Okay, so if you have that case, then because you see, if you have a gel phase resin, then there is diffusion going on in two distinct phases. There is the pore, and then there's the gel. Gel is much stronger electrolyte, as you can imagine. So one has to take that into account. The classic Boyd and Soldano work was completely uniform, one ion through one medium. That or I think I'll stop here, and when we return tomorrow, we will look at some cases of how to remove particular heavy metals from a particular background, and I'd like to talk a little bit about the other morphologies. We will talk of two morphologies, mainly the fiber and the sheet. And let's see what is there in the packet that was distributed to you. Let's see, day 4, Thursday. Heavy metal recovery, role of ion exchanger functional group, morphology of exchanger, equilibrium and kinetics. So I will spend some time on kinetics and regeneration, okay? And my focus during the discussion on regeneration would be how to separate a bunch of heavy metals from the regenerator, which is very common, okay? All right, so questions for today. Very good. So Urban will email you this file. We have covered from the chapter starts from page 45, and we are now on page, you can say, page 61. 61. Okay. So 45 through 61 is what we have covered, and 62 through 92 we will do tomorrow, and then we will look at the other morphologies. Okay. Thank you.